In this brief video, I'd like to explain how to solve second-order ordinary differential equations with Matlab. I've done an additional video doing first order. Now we're just going to take that to the next level and do a second-order equation. So just to have an example to work on, I'm going to look at a problem where you have a paratrooper falling from a height of 600 meters. The trooper is accelerated by gravity, and there's a drag force on the chute, and so the velocity of the paratrooper as he falls is governed by the balance between this gravity force and the drag force. And this came out of Cleve Moeller's excellent numerical computing with Matlab text. So the governing equation looks like this down below. F equals ma is essentially what we're doing. So m times the second derivative of y with respect to time is minus mg, that's the gravitational force, plus 4/15 v squared. I have to be a little careful with this, but for this problem, this form of the drag force is adequate. Velocity is assumed to be positive positive up, and that's why the gravitational force is negative. So y therefore is also positive up. So we can cast this as a generic second order differential equation where y double dot is some function of time, y, and velocity, or y dot. And for our equation, in order to write it in this form, we just divide by the mass. Then we have the second derivative of y is minus g plus 4/15 times v squared over m. Now that's a second order equation. Matlab wants to solve systems of first order equations, and this is the conventional way to do a typical Runge-Kutta solution. So we first have to convert the second order equation to two first order equations. We convert our boundary conditions into that, or our initial conditions into that form, and then we send it into Matlab and it solves it. The way we do this, the conversion to two second order equations, is by introducing a variable z, or at least the way I'm going to do it. Introduce z, which is the first derivative of y. So dy dt is z. And so what we're trying to do is solve for z and y as a function of time. So here's how it works. We set dy dt equals z. That's our first order equation. It's a first order equation, y dot, which is a function of t and y and z. In this case, it's independent of t and y, so it's just dy dt is z. If we take the first time derivative of this, we get d squared y dt squared is dz dt. If I flip that around, dz dt is the second derivative of y, and from our differential equation that we're trying to solve, we get minus g plus 4/15 times v squared over m. And v here is just z, right? V is dz, v is dy dt, which is z. Okay, so this will end up being minus g plus 4/15 z squared over m. Again, I'm a little cavalier in this term with sign, but for this problem, it works out. Our initial conditions then are at t equals 0, y is 600, assuming we're starting 600 meters from the ground, and z is 0. So that means we have 0 velocity. So the paratrooper just sort of steps out of an airplane or something and doesn't jump up or down. So initial velocity is 0. Initial position is 600. We're going to use the ODE45 routine. There's a half a dozen other initial value problem solvers built into Matlab. They all work pretty much the same way, but they have different solution techniques, either lower order or some include ways to solve stiff equations, things like that. This is probably the most heavily used routine. Uses a combination of fourth order and fifth order Runge-Kutta to do an adaptive solution to a problem. So what we have to give it is some function that defines the first derivative of y and of z. That is the first derivative of our two variables we're solving for. We need to provide the initial values, and we have to tell Matlab how long to solve this. So it helps to think of numbering your equation. So we'll let y be variable 1, the height of the paratrooper from the ground, and z be variable 2. And so we have to provide a function that returns a vector that for any y and z returns dy dt first and dz dt second, since that's the way we numbered our variables. So here's what I did. I called the function f. So f takes in a value of t and a vector y, which in this case holds our first variable y and our second variable z. So I'm mixing up y's a little bit, but I think you get it. So y in this context is a vector. The first element of the vector is the height from the ground. The second is the velocity. I provide the mass and gravitational constant as constants. Then I send this vector rk, which matches my output. Dy dt is z, which is y of 2. Dz dt is minus g plus 4/14 times v squared over the mass, or z squared over the mass. I use this dot operator because y in general could be a vector, and I want to make sure the math is done element by element. And here's how you do it. Once you get that set up, it's pretty easy. I set up a vector for the time range. It's a little 2 vector that says start at t equals 0 and end at 15, 15 seconds in this case. The initial values for the first variable y and the second variable z are given here. Then we say ty in brackets equals ODE45 of at f, where f is the function that provides the time derivatives, and then this time vector and the initial value vector. So that returns a set of times at which Matlab calculates both y and z, and then a vector of, actually a matrix that for each time gives a value for the first variable, height from the ground, and the second variable, which is velocity. Then I plot the height and give it labels, and that's it. And here's what the solution looks like. So that's basically it. If you want to generalize this to higher order, you can imagine how to do it. Otherwise, it's just a straightforward application of ODE45 after you convert whatever equation you have to a system of first order equations. Thanks.